curious minds. Welcome back to Project Silence Prodigy, your one-stop solution for project management and mechanical engineering needs. I'm Govind, a certified PMP and a mechanical engineering professional with more than 25 years of experience in the power and energy industry. In today's lesson, we will understand some of the most common terms used in a power plant. We often hear words like installed capacity, fuel types, base load, gross generation, net generation, availability, reliability, utilization. But what do these terms actually mean? To make everything simple, we will use one practical example throughout this lesson. Let us consider a 45 megawatt HFO based power plant using large medium speed 4-stroke engines. This plant has 5 gensets and each genset is rated at 9 megawatts. So this will be our example power plant. Plant installed capacity. Installed capacity means the total rated power of all generating units installed in the power plant. In our example, we have 5 gensets and each genset is rated at 9 megawatts. So 5 into 9 become 45 megawatts. Therefore, the installed capacity of this plant is 45 megawatts. But remember, this doesn't mean the plant will always generate 45 megawatts. It only tells us the total rated capacity which is installed in the plant. Generating unit or genset. A genset mainly consists of an engine connected to an electrical generator. The engine burns fuel and produces mechanical power, and the generator converts this mechanical power into electrical power. And in our example, we have 5 generating units, each of 9 megawatts capacity. Fuel used in engine power plants. Large engine power plants can use different types of fuel, and these can be liquid fuel, gas fuel, or dual fuel. Liquid fuels may include HFO, LFO, MDO, or diesel. In our example, the main fuel is HFO, heavy fuel oil. Depending on the plant design, diesel or light fuel may also be used for starting, stopping, or other operating conditions. Gas engine plants may use natural gas, LNG, biogas, or other suitable gases. If we talk about dual fuel engine, they mainly use gas together with a small amount of pilot liquid fuel injection. Dual fuel engines can also run fully on liquid fuel. Engine configuration and make. This refers to how the cylinders are physically arranged inside a large medium speed engine. L means inline engine. The cylinders are arranged in one straight row. For example, 6L means 6 cylinders in one row. 8L means 8 cylinders in one row. 9L means 9 cylinders in one row. Inline engines are generally narrower but longer than an equivalent V engine. In a V engine, the cylinders are divided into 2 banks, which are positioned at an angle to each other. When we view from the flywheel end or free end, the arrangement looks like the letter V. For example, 12V means total 12 cylinders. 6 cylinders in A bank and 6 are in B bank. 16V, total 16 cylinders. 8 cylinders in A bank and 8 are in B bank. Similarly, 18V, total 18 cylinders. 9 cylinders in A bank and 9 cylinders are in B bank. The main advantage of V engine is that more cylinders can be fitted into a shorter engine length. If we talk about maker, there are many well-known engine manufacturers in the power and energy sector that provides large medium speed engines for power generation. Some popular engine makers are like Wärtsilä, MAN, Cat MAK, Bergen Engines, and several others. Another important power plant terminology is plant operating duty. It simply tells us how and when a power plant is expected to operate. Based on its operating requirement, a power plant can generally work as a base load plant, standby plant, or peaking plant. A base load plant is designed to operate continuously for long periods and supply the regular power demand. Because it operates continuously, it normally has high running hours and high utilization. For example, if our 45 megawatt engine power plant is operating continuously throughout the day to supply regular electricity, we can call it a base load power plant. Standby power plant normally remains stopped, but it is kept ready to start whenever power is required. It is mainly used as an emergency or backup power source. For example, a factory is receiving its normal electricity from the power grid, but it keeps a diesel power plant ready as backup. If suppose the grid supply fails, the standby engines start and supply power to the factory. Since standby power plants operate only when required, they normally have low running hours and low utilization. The third one is the peaking power plant. A peaking plant operates when the electricity demand becomes temporarily very high. For example, suppose the normal grid demand is 500 megawatts, but during evening hours or peak hours, it increases to 540 megawatts. So in this case, our 45 megawatt engine power plant can be started to support this additional demand. Engine-based power plants are well suited for peaking duty because they can generally start quickly and respond to changes in power demand. Once the peak demand is over, the plant can reduce its load or simply shut down. Megawatt and megawatt hour, MW versus MWH. This is a very important difference. Megawatt means power. It tells us how much power the plant is producing at the moment. And megawatt hour MWH means energy generated over time. 1 megawatt is equal to 1000 kilowatt. So 1 megawatt hour is equal to 1000 kilowatt hours. If our plant runs at 40 megawatt for 10 hours, so energy generation will be 40 into 10 is equal to 400 megawatt hours. So remember, megawatt is power, but megawatt hour or kilowatt hour is energy. Gross and net generation. Gross generation is the total electrical energy produced by the generators before deducting the plant's own electricity use. Suppose the plant runs at an average of 40 megawatts for 24 hours. So 40 into 24 is equal to 960 megawatt hours. So the gross generation is 960 megawatt hours per day. Then comes auxiliary consumption. A power plant also uses some of its own electricity. And this electricity is used by auxiliary equipment like cooling water pumps, fuel transfer pumps, pre-lube oil pumps, air compressors, cooling fans, fuel treatment equipment, ventilation, lighting, and control systems. This internal electricity use is called auxiliary consumption. Suppose the plant generates 960 megawatt hours and the auxiliary consumption is 38 megawatt hours. So if you calculate it in percentage, then auxiliary consumption comes around 3.96%. And the final comes net generation or exported power. Net generation means the energy left after deducting the plant's own auxiliary consumption. So net generation will be gross generation minus auxiliary consumption. So in our example, 960 minus 38, which will be 922 megawatt hours. So the net generation is 922 megawatt hours per day. And this is the energy which actually sent to the grid. May also be called exported energy or net export. Availability, reliability, and utilization. Another three very important terms which are used to measure power plant performance. To understand these terms easily, let us continue with our power plant example, which has total installed capacity of 45 megawatt. And it consists of 5 generating units of 9 megawatt each. Let us consider the plant performance for 1 month, which is 30 days. So the total time available in the month is 30 multiplied by 24, which is 720 hours. Now suppose during these 720 hours, the plant was running for 600 hours. And it was on standby and ready to run for 80 hours. It was stopped for plant maintenance for 25 hours. And it had a forced outage for 15 hours. So 600 hours running plus 80 hours standby plus 25 hours planned stoppage plus 15 hours forced outage gives us 720 hours. First term is availability. In simple words, availability tells us was the plant ready and capable of generating power when required. Availability considers both running hours and standby hours. Why? Because even though the plant is not generating during standby, it is still healthy and ready to start when required. The formula is availability equals running hours plus standby hours whole divided by running hours plus standby hours plus stop time multiplied by 100. In our example, running hours are 600, standby hours are 80. So the plant was available for 600 plus 80, which is 680 hours. And the total stoppage is 25 hours planned maintenance plus 15 hours forced outage. So which gives us 40 hours. So availability will be 680 divided by 680 plus 40, which is 720. So 680 divided by 720 multiplied by 100. So it gives us approximately 94.4%. So even though the plant actually operated for only 600 hours, it was available for 680 hours. Because during those additional 80 standby hours, it was still ready to operate. Now let's understand reliability. Reliability is the probability that equipment will perform its intended function for a specified period under stated conditions. In simple power plant language, reliability is can we depend on the plant to operate without an unexpected failure? For reliability, formula is running hours plus standby hours whole divided by running hours plus standby hours plus forced outage hours into 100. Notice the difference here. For this reliability calculation, we are mainly concerned with the forced outage. In our example, running hours are 600, standby hours are 80, and forced outage is 15 hours. So 600 plus 80 equals 680, which will come in numerator. And denominator will be 680 plus 15, which will be 695. So 680 divided by 695 multiply by 100. So this will give us 97.8% reliability. You might have noticed that in our example, reliability is higher than availability. Because when we calculated availability, 25 hours of planned maintenance reduced our availability. But in the reliability, planned maintenance is not included as a forced failure. Reliability is mainly concerned with the plant's ability to perform its required function without unexpected failure. Utilization. Utilization tells us how much the plant was actually being used. It expresses the amount of time the engine has actually been in use during a certain period. And the formula for utilization is running hours divided by running hours plus stoppage hours into 100. In our example, running hours are 600 hours and total stoppage is 25 plus 15, which is 40 hours. So 600 divided by 640 multiplied by 100 gives us 93.75% utilization. So utilization asks how much was the plant actually used. So that brings us to the end of part A of our power plant terminology lesson. In part B, we will continue with some more important technical and performance terms which are used in day-to-day power plant operation. If you found this lesson useful, please like the video and share it with your fellow engineers. And subscribe to Project Excellence Prodigy for more practical lessons on project management and mechanical engineering topics. Namaste, goodbye, Sampai Jumpa.